Welcome back. Today we're going to take a look at conditional probability, and I do have one little thing I just want to make a correction about from the last lesson. It's not actually technically wrong, except that it made a reference to something that's a little wrong. I mentioned that the last lesson on mutually exclusive events and this lesson are often mistaken for each other. It's actually mutually exclusive events and our next lesson, 4.5, that often get mistaken for each other. This one here is kind of a little in between that's needed to understand the next topic. But yeah, just in case you're wondering how this relates to mutually exclusive events, it doesn't. Although that was kind of my point about the next lesson anyway, is that they're not the same thing. But just so you know, the next lesson we're going to try and convince you why it's not the same thing as mutually exclusive. Today we're going to talk about conditional probability, which really means what's the probability of something happening if you know information about the event that occurred. Whether that's important information or not important information may change our answer, but in many cases it will change what our answer is. So just as kind of a classic example, if you were standing in front of me and I had a deck of cards and I drew one card and looked at it, and I asked you, what is the probability that this is a king? Most of you would be good enough at statistics so far or at probability so far to realize that, well, there's 4 kings in the deck, there's 52 cards. That's 1 out of 13. So there's a 1 in 13 chance that I'm holding a king. Now, here's a little interesting thing. Let's say that you actually notice the reflection of the card just a little bit off of my glasses. You can't quite make out what the card is, but you've narrowed it down. You're positive it is a face card. If you know it's a face card, that does change the probability that it's a king, because it's either a jack, a queen, or a king, and now knowing that it's a face card can limit your probability to a 1 in 3 chance of being a king. So there's an example of where knowing a little bit of information about what's happened can let you change the probability of something else happening. There's a classic commercial, and I've been looking for it on YouTube for years, but I can't find it. It's 2 insurance agents that are walking down the street, and one of them goes to step on the road, and the other one grabs him and says, do you know what the probability is that you're going to get hit by a car in this intersection? And just as they're saying that, a guy wearing like pilot goggles and a suit rides down the street beside them on an ostrich. Is really kind of a weird scene. And the guy who almost got hit by the car looks over and says, what's the probability of that happening? And the other guy says, now 100%. And he's absolutely correct. What is the probability of someone riding down the street on an ostrich, given that someone's riding down the street riding an ostrich? It might have been low before, but given that information, it's now a 100% certain item. So a great example of conditional probability. That said, let's take a look at the new notation. What we have here, this notation, we just have a vertical bar. And that vertical bar is going to represent, or at least we're going to read this as the probability that A occurs given that, this is where the bar comes in, given that B has occurred. So what's the probability that A will occur given that B has occurred? So the equation that we're going to use for the probability of A given B is just the probability that A and B have occurred divided by the probability that B occurred. Or I should say A and B will occur, because I don't know if they've happened or not yet. Now, I want you to note that probability is just the number of ways things can happen divided by the number of things in the universal set. And since both of those would be divided by universal set, I could write this down just as the number of ways that A and B can occur divided by the number of ways B occurred. Those are really the same equations. I just converted the probabilities into number of ways divided by NS. And since the NS's top and bottom cancel, those are equivalent. Now, before we go too much further, I also do want to point out that the probability of A and B occurring is non-communicative, which means that the order does matter. So for instance, with unions, A union B and B union A mean the same thing. Likewise, intersects, A intersect B and B intersect A mean the same thing. Just means both criteria have been met. A given B, the probability of A given B is not the same thing as the probability of B given A. So just as an example of that, that's logically easy to follow, if A was the event that I die and B is the event that I'm thrown into the sun, the probability that I die given that I'm thrown into the sun is 100%. At some point in the future, some human being may be thrown into the sun and die, but right now there's no one ever been thrown into the sun and survived, mostly because there's no one ever been thrown into the sun. But probability that I die given that I'm thrown into the sun, 100%. Reverse those. The probability that I'm thrown into the sun because I have died is not 100% because again, no one has ever been thrown into the sun before. So reversing those definitely changes the outcome. So they are non-communicative. Order does matter. And just looking at the equation, you'll notice that the top A and B is going to be the same if I reverse the two. That'll be B and A. Intersect doesn't matter. However, the bottom of the equation will change from the probability of B occurring to the probability of A occurring if I switch the order of A and B. And if those are different, then this answer will also be different. Okay, so let's just try a couple examples and see how this actually works. What is the probability of rolling a sum greater than 7 on 2 dice? Okay, let's do the dice table. You guys may recall this from an earlier lesson. I'm going to just try to do it as quickly as I can. It's not going to be the prettiest, but it doesn't need to be. First roll is going to be a 1, 2, 3, 4, 5, or 6. Second roll is going to be a 1, 2, 3, 4, 5, or 6. And then the sums are going to be so on. And again, how you fill in this table is completely up to you. I kind of jump around because I've drawn so many of them. And just a little bit later, we're done. There we go. Okay, what is the probability of rolling a sum greater than 7 on 2 dice? Now, sum greater than 7 on 2 dice, let me just really quickly take a look at this. Sum greater than 7 means it has to be 8, 9, or 10. So 8s, 9s, 10s, 11s, 12s, those are all greater. Now also note that this is not actually a conditional probability question. There is no condition of something has already happened. It's just saying what is the probability of getting a sum greater than 7 on 2 dice. And we can just basically look at it and say, well, it's the number of red circles we got. That's the number of ones that met the criteria. And there are 15 of those. And there were 36 possible outcomes we could get, 36 possible pairs of numbers. And so that, when we write it as a percentage, is just going to be 15 divided by 36 is 41.7%. And I'm always rounding off pretty much to one decimal place. I think it's 0.6 repeating. But good enough. Part B, what's the probability of rolling a sum greater than 7 if it's known that the first die rolled is a 3? Okay, let's see if we can do this using the equation up here, this one. And I'll tell you right now that most of these is actually going to be easier to do brute force. Let's try one using the proper equation and try it doing brute force and see what we get. So the probability of, again, this is, we want a number greater than 7 if we know the first die roll is a 3. So probability greater than 7, given that first is a 3. Not exactly the prettiest notation ever, but it gets you the idea. And we said that that's equal to, should be the probability of both, greater than 7 and first is 3. I could have used the intersect symbol instead of and. Actually, I probably should, just to be more proper with our equation. But really, that's what the intersection means, is both criteria have been met, divided by the probability of B, which we actually know is the first number is a 3. Okay, so what is the probability of getting a number greater than 7 given that the first number is a 3? Sorry, probability of rolling greater than 7. Let me try this one more time with my words. What is the probability of getting a sum greater than 7 and the first roll being greater than 3? So how many ways can that happen? So I look in my table and I say the first number has to be a 3 and it has to be greater than 7. So I think that's just, let me change color again. Use green this time. First roll is a 3, that's right here in this column. And the sum greater than 7 is this 8 and this 9. So there's 2 out of 36 ways both of those happen. So 2 out of 36. And this is one example where I'm just going to leave it as a fraction for now. You'll see why in a second. And the probability that the first is a 3 is, well, the first is a 3, 6 of the outcomes. So basically everything in this column, 1, 2, 3, 4, 5, 6. 6 of 36 outcomes. And luckily, the 36s cancel. Basically, 2 out of 36 divided by 6 out of 36 is just 2 out of 6, which is a 33.3% chance of happening. Now, another way that you can approach this problem is to just actually brute force attack it and say, wait a second, the probability that the sum will be greater than 7 given that the first number is a 3. Well, if the first number is a 3, that's not a choice. It's been prescribed. We're told that happens. So there's really only 6 possible outcomes. So these are the only 6 possible outcomes because we know the first roll was a 3. And then we're being asked, what is the probability that there's a number greater than 8 in that? And the numbers greater than 7 in that are the 8 and the 9. So the probability of, and I'm not writing that again, so I'm just going to write down A given B. The number of ways we get what we want is the 8 out of 9, that's 2. The number of ways we could get that outcome is 6. And that much, much quicker gets us to 33.3%. So I think in most cases, you're going to want to brute force these, keeping in the back of your mind that there is actually an equation to be used. But if we can just basically limit it by crossing out scenarios that don't happen. So as an example, well, actually, let's just keep doing examples because it's going to pop up some more. Okay, question 2. A large group of families that all have 2 children is being surveyed. Find the probability that the family has 2 boys. Now, I do want to point out that this one's not actually a conditional probability problem, although the others are. So I just want to kind of see how the unrestricted or no known information part takes place. So we have 2 children, and there's basically a few possible outcomes. We could have 2 boys. We could have a boy and a girl. We could have a girl and a boy, or we could have 2 girls. And we'll say that the first one is the oldest child, the first child, and the second column, it represents the second child or the youngest child. Now this one's pretty straightforward. The probability of getting 2 boys, well, there's 4 scenarios. So that's how many things are in the universal set. And there's only one that meets our criteria. That's 2 boys. So that's 1 way out of 4 possible ways, gives us 25%. Pretty straightforward. Okay, for part B, find the probability that the family has 2 boys if it's known that the oldest child is a boy. So the probability of 2 boys given oldest is a boy. We can again go to our formula, but I think you'll find that in most of these scenarios, brute force is much easier and is better and easier to understand. So what we're going to do is just list the possible outcomes we can have again. Boy, 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 girl, girl, boy, girl, girl. So before it was 1 out of 4 because we had no information. Probability of having 2 boys was 1 out of 4. But here what we can do is use our conditional probability to say, can we eliminate any of those possibilities as being no longer valid outcomes? Is it possible to have a boy and then a boy? Yeah, the oldest would be a boy. Sure, yeah, that works. What if the oldest is a boy and the youngest is a girl? Well, that's valid. Well, the third one is a girl is born first and then a boy. Well, then the oldest would be a girl. This can't happen. And can you have 2 girls if the oldest is a boy? Nope, that one's gone too. So now we only have 2 scenarios left that are valid, and one of them is what we're looking for, the probability of having 2 boys. So this one's just 1 out of 2 instead of 1 out of 4. And that's 50%, obviously. Now, of course, you can think about this in a slightly different way. If the first is a boy, then really all we're looking at with this conditional probability isn't the probability of having 2 boys given the oldest is a boy. It's what's the probability that the second child's a boy. And this probability of the second child being a boy or a girl is 50%. We don't need to worry about what the first child is because it's already happened and it's already led towards our criteria that we need. A very similar question, but not quite the same. Find the probability that the family has 2 boys if it's known that at least one of the children is a boy. So probabilities of 2 boys, given that 1 plus boys. Again, notation doesn't really matter as long as it's descriptive. And we can write out our criteria. Boy, 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 girl, girl, boy, girl, girl. Now, of those 4 criteria, we're told that at least one of the children is a boy. There's only one of those scenarios that isn't possible, and that's both children are girls. So given that the remaining 3 are all possible scenarios, you either have 2 boys, a boy then a girl, or a girl then a boy. One of them has 2 boys, so this is a 1 in 3, or a 33.3% chance of happening. Okay. Question 3 is an interesting one. I'm going to read it and then give you a moment to think about it because it's just interesting. Okay, the probability that Marge will go to Springfield Community College is 1 in 5. And if Marge goes to Springfield Community College, the probability that her boyfriend Homer will go with her is 3 out of 4, or 75%. What is the probability that both Marge and Homer go to Springfield Community College? Okay, well, you're welcome to try and brute force your way through this one, and many students do. This is one where I think maybe using the equation is helpful. So what I'm going to do is say, what is the probability that Marge goes to Springfield Community College, if Marge goes to Springfield Community College, the probability, so Homer, what's the probability that Homer goes given that Marge goes? That's really the information we're given in the question. And according to our equation, that should be equal to the probability of Homer and Marge, both going, divided by the probability that Marge goes. So now the interesting thing about this one is it's not the probability, the conditional probability that we're looking for. The conditional probability has been given. We're looking for the probability of H and M, both Homer and Marge going to Springfield Community College. So as we fill in these numbers, if Marge goes to Springfield Community College, then the probability her boyfriend will go is 3/4. Well, that's this left-hand part. Homer, given that Marge goes, is 3 out of 4. we're looking for the probability of Homer and Marge. And the probability that Marge goes is 1 in 5. So now if I want to find the probability of H and M, I could just multiply both sides by 1/5. That's 3/4 times 1/5. So the probability of H and M is going to be 3 times 1 over 4 times 5, which it works out to be 15%. So the probability that both of them go is 15%. Now, if you're someone who saw the brute force logic in that one and you want to go with the brute force logic, by all means, feel free to. If you're somebody who's having a hard time seeing it, remember you can rely on the equation. I find that, I don't know, in 3/4 or 80% of situations, I find brute force to be the easier way to approach these. And in 20 or 25% of situations, I find it easier to go with the equation. Whatever you find easier, you do. You do you, baby. Okay. Question near and dear to my soda drinking heart. A pop machine is broken and randomly dispenses a flavor of pop with the following percentages. This, by the way, this question is loosely based on the pop machine that was in the Eastwood staff room for some number of years. I'm pretty sure it's been there since the late 70s or early 80s. It's just a bucket of crap. I can't believe it still works, but luckily we don't have to pay the company anymore because they forgot we have it. Someone changed jobs and they no longer have a record of us, so that's perfect. Okay, so 35% of the time it dispenses Coke, 25% of the time it dispenses Diet Coke, 20% of the time it gives a Sprite, 15% root beer, and 5% Orange Crush. So what is the probability that you'll get a Diet Coke if you know it's not root beer or Sprite? So probability of Coke or Diet Coke, given that not root beer or Sprite. Is that pretty notation? Not particularly. So here's the way I want you to think about this. I want you to look at the list above and say we've got 35, 25, 20, 15, and 5. However, something has changed. Because we know that root beer and Sprite are no longer being dispensed, those are no longer possibilities. They're off of our list. Now what I want you to do is forget the fact that things should add up to 100% when you put them all together. And rather than redistribute those percentages, just take them as they are and say, okay, what's the probability that you get a Coke or Diet Coke? And that would be 35% plus 25% over the probability that you get anything other than a root beer or Sprite. And that would be 35% plus 25% plus 20%. So we no longer have root beer and Sprite on the list, but that's okay. Okay, so the top is just 60%, the bottom is 80%, and I could put the percent ons or not, because they both mean divide by 100, they cancel top and bottom. So whether they're there or not, the ratio is still 3 to 4, and you get a 75% chance. So without root beer or Orange Crush coming out, you know that that hasn't happened. You can now say that there's a 75% chance you'll get a Coke or a Diet Coke. Okay, I'm going to remove these lines up at the top here, just because we're going to move on to part B. Part B is, what is the probability that you'll get a Diet Coke if you know you're getting a Coke or a Diet Coke? We're going to use the same logic that we were before and say if we're getting a Coke or Diet Coke, those three are not options anymore. Just cross them off the list. They didn't happen. So now the probability that I get a Diet Coke, given that I get a Diet Coke or Coke, and again, if you just want to do A given B and not put these descriptions in, that's fine too. It's just going to be 25 over 35 plus 25. And again, leaving the percents off there doesn't change anything since all you're really doing is multiplying top and bottom by 100. That's okay. And so that becomes 25 out of 60. And my calculator tells me that 25 divided by 60 is 41.7%. So there is a 41.7% chance that I'll get a Diet Coke knowing that it's either going to be a Coke or a Diet Coke. And this idea of canceling out things that it can't be and then working with what's left is actually a much more powerful rule in most cases than going back to the definitional equation. So feel free to use it. Whether you physically, literally cross things out like I just did on this list, or you just mentally don't count them or don't include them in your answer. As long as you're getting the right answers, I'm happy. Speaking of getting right answers, you won't know whether or not you're getting the right answers using the method of your choice until you try some questions and use the method of your choice. So go do that. Let me know how it goes and what timing, what perfect timing since my screen just died. Anyway, we'll catch up with you in the next lesson. Have a great day.